Okay, so we're at time. Let's get started. So hey everyone, welcome to join this another CelerData webinar. My name is Sida Shen. I am a product marketing manager at CelerData. Today we're gonna talk about something very exciting. We're gonna talk about data lake and data lakehouse, specifically Trino versus StarRocks, and how to get data warehouse performance on the data lakehouse. Right. So here, let's get started. If you have question, by the way, just post them in the chat, and I'll address them at the end of this webinar. So here is the agenda. So first, I will talk about the status quo of data lake analytics. So specifically, the cost of slow queries on your data lake, right? And then I'll talk about the challenges when it comes to data lake queries when it compares to traditional data warehouse or OLAP database, right? How is it different on the database side, optimization side, right? And then we'll go to talk about Trino, right? Gonna talk a little bit about Trino's performance and how is it kind of falling behind. And also we're gonna take a tactical look into Trino's data lake query performance and some of the optimization they do and some of the optimization they're not doing, right? Or they're planning to do, right? And then we're gonna go talk about some newer generation query engines, StarRocks, for example, right? And then we're gonna do a technical comparison, benchmark comparison between StarRocks and Trino, and then we're gonna look at 3 success stories from industry leaders, including Trip.com, right? And how they're going with data lake analytics, right? Let's get started. So first, data lake analytics, the status quo, right? Data lake, when you talk about data lake is, in my opinion, is on a cloud object storage or on HDFS, right? So it's very cost effective and is the one place that we just store all kinds of data in there. We just throw it in and forget about it, right? And when we need it, we kind of fetch them into a tool that is designed for that kind of workload, right? And do that, right? But there have been a lot of development in the data lake field, especially in the past few years, right? With the new emerging data, like open lake table formats, for example, Apache Hudi, Iceberg, and Delta Lake, right? They're giving data lakes, data warehouse-like features, such as transactions and schema evolution, compaction, time travel, and DDL support, right? Um, so they're kind of making, they're kind of building houses on the lake. Uh, so they're making data lake house, right? So it's basically a great combination of the features of data warehouse plus the cost effectiveness and scalability of data lake, right? So it's safe to assume that data engineers are developing analytics workloads on the data lake house, right? Or are they actually doing that? So from my experience, I'm kind of active the StarRocks community, the open source community, as well as talking to our clients, CelerData. That's really not the case, right? The reality is users are still copying their data out of the data lake purely for query acceleration purposes, right? Like in this image, you can see people moving little boxes out of this house. So that's taking the data out, taking the workload out. Hope that was clear. And the reason being, existing data lake query engines, they're not performant enough for a lot of the more modern workloads, right? They're either not optimized for high concurrency or low latency workloads, still optimized for batch, talking about USpark, or they're still on older technologies, right? They're not taking advantage of all of the crazy optimizations we can do with modern software and hardware, specifically hardware, right? So they're not able to handle some very demanding analytics workloads on the scale of data we have, and on the workloads such as customer-facing analytics, where the concurrency and latency requirements are insanely high, right? So as a workaround, users are still forced to move the workloads to a high-performance data warehouse purely for query acceleration, right? This does really solve the problem. It makes the query fast, but it also introduce a lot of challenges and a lot of costs that's involved, right? So the first is that you're introducing a data warehouse. So that's a infrastructure level software. No matter how easy the deployment is, it's still a database, right? A database is stateful and is kind of expensive to maintain, right? And also you have to consider the cost of the data ingestion pipeline, right? Data ingestion not only to maintain this pipeline, but writing your files from a open file format like Parquet to a proprietary file format that takes a lot of CPU power as well, right? And also it introduces lag to your data freshness, right? And make your data less fresh. And also there's challenges, integration challenges, matching the schema, the data type, sequels, and blah, blah, right? Etc. Etc. And also you're copying your data. You're not keeping your single source of truth on the data lake, right? You're copying your data into somewhere else, and you have to somehow keep them in sync with all of the appends, even data updates that's happening, right? And that can introduce a lot of data governance challenges from doing that, right? So how to make data lake queries run faster, and how is it different that to optimize a data lake query when compared to a traditional data warehouse query, right? So the main cost of data lake query mainly come from fetching the data from your external storage, from your cloud object storage, cloud, and fetching the metadata from your metadata store, right? And this is much more expensive than scanning the data on your local disk, with a data warehouse, right? And this can much more easily become the bottleneck of the whole query. Even, in some cases, the queries are extremely complex. It's supposed to be CPU heavy, but it can still bottleneck on the data scanning part, right? So the first is the slow and unpredictable performance of data lakes. Uh, so if on the cloud, right, we're using cloud object storage, they're fast, but they're fast in terms of throughput, right? If you have a really large file, you can uh, transfer it, upload it, or download it from the object store really fast, but they're not really responsive. So the latency of cloud object storage is much higher than the local disk. It can be, somewhere in the higher tens of milliseconds to 100 milliseconds, right? Also, data files can be optimized for query, right? It's a data lake after all, right? Sometimes it can be without compaction. You can have a lot of small files, and that's not really good for query, right? And for some table formats, you have lack of control over your data distribution, right? Some of them don't support bucketing and cannot prune your data, and sorting, and also co-located joins. Some of them don't support those. So it's kind of unique for data lake challenges. Not all of the pressures on the CPU, like like we we think, right? Now let's talk about Trino and Trino's performance. So what is Trino? Trino is an open source distributed SQL engine, right? I think when I first know about Trino and Presto, it's with its connectivity to different data sources, right? It's great for doing that, right? It's written in Java and it's forked from the Presto project, right? And Trino was actually really a game changer for data lakes when Presto was introduced. Presto Trino was introduced. It has an MPP architecture. It's not really. It supports data shuffling and it supports in-memory data shuffling, unlike those MapReduce frameworks, right? And MapReduce, we hear a lot about, map, very slow shuffle, reduce. That's because the shuffling operation is expensive, but like MapReduce is designed for large ETL workloads that runs for hours, right? So during the self-shuffle operation, actually persists all of the intermediate results to disk for stability reasons. So it's not really optimized for low latency queries. But Trino's architecture supports in-memory data shuffling, and that's actually by itself. That's a great design for low latency queries. And that was a game changer at the time. It brought query latency from hours or higher in the tens of minutes, 2 minutes, lower minutes on massive amount of data, right? If Trino doesn't go OM, right? And then, but the performance of Trino is actually falling a little, falling behind for all of the intense workloads that we try to throw at them. Data warehouse, low latency, high concurrency workloads. And now we're gonna bring up a kind of like a newer generation query engine as a comparison, right? StarRocks is a query engine, and that also features a MPP architecture, and it's written in C++, SIMD optimized, right? And it's sub-second. It's really good at performing sub-second queries at scale with high concurrency, right? So you can run your demanding data warehouse workloads, all of your workloads, SQL workloads on the data lake, right? So let's first take a look at some performance numbers. So the benchmark is TPC-DS 1 terabyte. TPC-DS resembles a kind of like a more complex query scenario, right? It's more like some ad hoc queries where you have a lot of joins across many tables, as well as a lot of high cardinality aggregations, right? It's quite challenging for the query layer. And StarRocks is 5.5 roughly times faster than Trino on this benchmark test on the same exact data stored on S3 and managed by Iceberg, right? So what is causing this performance difference? Why Trino is kind of falling behind in terms of performance? So raw performance wise, most of the performance difference is from Trino's Java-based framework, right? It's written in Java, and it's difficult to take full advantage of the SIMD optimizations, right? So SIMD is single structure, multiple data. So we can take this image as an example, right? So you have two vectors, and you perform addition between scalar addition between the two vectors, right? And for optimization of this, what we're trying to do is we're trying to decrease or minimize the amount of memory seek there is, right? Because when compared to CPU and CPU cache, memory is a lot slower, right? So without SIMD, you can see that each number or each value in the vector requires a seek memory, and as well as as well as each of the compute, right? So everything is processed in series instead of in batch, right? But with SIMD, you can get many data values with one memory seek, and that significantly decrease the number of memory seek, thus increase the overall performance, right? And also the reason why a lot of OLAP database or query engine or storage engine use columnar storage is because like in OLAP, we always get values by column, right? And then we create bigger batches if we store them in a columnar fashion, right? And also plus vectorized execution is the same, right? And that's basically storing everything in memory in a columnar format, right? So without SIMD optimization, those two, we can lose a lot of performance gain if we don't really have SIMD in there. But it's silver lining for Trino, if I'm being completely honest. Trino is moving to Java 21, which gives Trino the ability to utilize some SIMD instruction sets, but still kind of limited, right? and the work that takes to make all of your operators SIMD that's a lot of work in there, right? Because we've done it. And yeah, and with Java is even with Java 21 is impossible to get the same amount of optimization done compared to your applications written in completely in C++, right? And also, we talk about the unique challenges of data lake queries, right? Scanning data, fetching data from external storage from data lake can be very expensive. It's easily become the bottleneck in the entire query path. Even the query is complex with joins and aggregations, right? And Trino itself is not really equipped with a mature built-in caching framework. It has a Hive connector cache, but that's not really mature and I presume only work for Hive, right? And the only option is to introduce an external framework that takes care of this problem, right? But it causes more problems. So first, it is another software that needs to be maintained, right? For example, you can use Luxio as a caching layer, right? And also, there can be data transfer cost between the two services, and that can presumably cause network overhead sometimes. Well, like when compared to a built-in cache, which runs in the same process as the query engine, right? That's the most optimized way to do it, right? And also, there's integration challenges with the caching layer, right? Remember, it's one time I used Trino with Elixir, right? You even have to change its create table format, create table SQL, right? And it's not really a very smooth experience. It's not a seamless experience, right? And also with the external caching framework, it's very difficult to, or sometimes impossible to implement some lower level caching, such as page cache, right? And then let's take a look at StarRocks and see how StarRocks is doing things differently to get the performance increase, right? The performance advantages. So StarRocks is a new generation query engine, right? It has a very simple architecture with only two kinds of processes. So you have the FE and the BE, or the compute nodes, right? And it's the same as Trino. It features MPP with in-memory data shuffling, plus fully vectorized execution engine, execution framework, right? But one thing that's different is that it's B, so the execution layer is completely written in C++. So that's make us very easy for us to take advantage of all of the SIMD optimizations, right? We actually have some good performance numbers, when compared to a fully vectorized data warehouse, right? We're 2 times faster than ClickHouse, like as a data warehouse on single table queries on the SSB dataset, right? And it also has a built-in hierarchical caching layer, right? That's based on both memory and disk, and that's something that Trino does not have yet, right? And also StarRocks is inside SQL compliant, and also Trino dialects also has Trino dialect support. So if you want to test, if you're using Trino and want to test StarRocks, the only thing you need to do is deploy StarRocks cluster, right? And you don't even need to change the SQL and connect to your data lake, and you can start querying right away, right? And what I've talked about in the last slide, they kind of uh, only includes why stars is fast on the raw performance wise, right? And that's also what the benchmark already said. But what makes stars very different is let's go beyond. Let's go beyond, raw performance, because on the data lake, there's only so much optimization we can do, right? So I want to kind of introduce StarRocks materialized view and how that seamlessly accelerate data lake queries for StarRocks, right? A materialized view, for the audience that's not familiar with this term, a view is basically a logical representation of a SQL query, often a SQL select query, right? And the materialized view is the result of a of a SQL query, right? So it's like doing pre-computation, right? And for StarRocks materialized view, if you create a materialized view on the external data on data lake, it writes that into StarRocks' own format for query acceleration, right? So taking full advantage of StarRocks' own storage engine, that's you can do collocated joins, indexing, low cardinality optimizations, as well as bucketing, all of those that's not available, fully available on the data lake, right? And also, the materialized view of StarRocks fully supports query rewrite, which means that if you materialize view name is something else, and during the query, you don't need to change your SQL query script, right? It's gonna automatically route to the most suitable materialized view there is to do query acceleration, right? So if you say you have a query that joins two tables together and do some more calculation, right? And on the other side, you create a materialized view that join the two tables and create a flat table on the other side, right? You don't even have to change your original SQL script to let it benefit from the materialized view, right? So the whole process is seamless. And it also supports single table and multi-table queries, right? So you can, accelerate you can perform denormalization and you can perform pre-aggregations with StarRocks materialized view, right? And there's another piece that's very important. Remember when I said StarRocks is MPP with in-memory data shuffling, right? So one of the reasons why StarRocks is fast is because everything is processed in memory, same as Trino, right? But to perform data transformation, especially let's say denormalization, you join the two tables together, right? When you do that, you're probably not writing a predicate, right? So the join between two large tables, that takes a lot of memory. But StarRocks has this feature called operator spilling. So during query execution, if the memory is not sufficient, StarRocks can intelligently spill intermediate results to disk to prevent OOMs and ensure large data transformation jobs can run smoothly without OOM, right? And this is great. And this is what a lot of our users use to get great performance on the data lake without moving their data, right? And for this topic, we actually have another webinar that introduces dedicated to materialized view. That's in 2 weeks. And guys, if you're interested, please go sign up, right? Even you cannot attend, we're gonna send you the on-demand afterwards. So go sign up. It's gonna be fun, a lot of fun. Right? And here, let's go into some use cases and what industry leaders are doing in terms of data lake analytics. So first, let's take a look at Trip.com's Artnova platform. So Artnova platform is their internal reporting platform, right? It has a lot of data and runs a lot of queries every day. So this is its older architecture. They've been the StarRocks user for a very long time. And they actually started using StarRocks as a data warehouse. So they had Trino as a query engine, right? And because Trino is not performant enough for a lot of their scenarios, so they were forced to deploy another data warehouse, a StarRocks cluster on the side, and ingest the data into StarRocks purely for query acceleration purposes, right? And that was kind of creating some headaches for them. So first, despite StarRocks ingestion, data ingestion speed was pretty fast. The data freshness still lags because of the data ingestion, right? And that affects the flexibility and timelessness of the queries. And it also adds complexity in the data pipeline, right? Because you are maintaining two systems and with the ingestion pipeline, and the table schema index design has to be the same, right? And you have to do like additional table schema design and index design, right? and also duplicating the data to another data warehouse. You're the same data having 2 copies. That's not really great for data governance, right? And that's kind of complex and very expensive for them. And then they kind of unified StarRocks as the sole query layer and got rid of Trino, right? By doing that, they first thing is they got rid of one big infrastructure level software on their technology stack, right? So they have a more streamlined architecture, and they experience a 7.4 time performance gain on the same data without the materialized view, the use of materialized view, right? The 7.4 times performance gain. And also they're keeping their single source of truth of data in their Hive tables, and that's great for data governance. And the next case I want to talk about is ATRenew. ATRenew is a listed company. Probably not a lot of people have heard of them, but they do great things. So they do environmental protection by recycling goods, mostly electronic goods, and they're listed on the New York Stock Exchange. So their story was, before they were trying to design their data architecture, right? They have 2 choices. So the first one is they have Hive, that's all of their data. So whatever they do, they sync all of their data into Hive, right? They have 2 options. First is to have OLAP database, ingest all of the data into the OLAP database, or they can have a query engine that's directly query the data in Hive, right? Their problem was the data volume. They have hundreds of terabytes of data per day, and for some table, they store the data up to 5 years. So that's a stupid amount of data and just not really acceptable to ingest that volume into a data warehouse and store it there, right? And also another problem there is that the queries often scan half of the entire data set, half the entire table. So they cannot really do hot cold separation when like half the data is hot, right? So and also they have 30 to 40,000 Hive tables. So their only option was to introduce a query engine and directly query Hive, right? So they brought in Trino when they just designed the system, right? But Trino is getting less performant. And then they tested StarRocks. According to their test on the TPC-DS benchmark test, with the same hardware and querying the same data, StarRocks is 16 or close to 17 times more performant than Trino under 20 parallel queries, under 20 concurrency, right? And that made them switch to StarRocks. And in production, because not all of the queries are CPU heavy, so 80% of the query experience at least a 2-time performance gain, right? And this number, keep in mind, they didn't even have the cache turned on. So they're planning to do that. And when they do that, it's going to be even more of a boost. And the third and final case study we want to look at is Red. And Red is a social media company that has 200 million plus monthly active user, right? And they have been a StarRocks user from the beginning, if I remember correctly. They use StarRocks for real-time analytics and on a really large scale, right? They have, like right here, they have more than 100 billion rows of real-time data ingested per day on 30,000 plus CPU cores, and the average latency is 200 milliseconds, right? And that's their real-time customer-facing use case. But they also have another use case that's like internal reporting analytics, right? On Hive. The scale of data on their Hive is stupidly big. It's on the EB, I don't even know how to pronounce that, 1,000 petabytes plus, and they have 10,000 plus Hive tables, right? And before they were using Presto for that case. Because they were already using StarRocks, so they already have to maintain a StarRocks cluster, And also they have to maintain a Presto cluster, right? That's too many technology stacks to maintain for their use case, right? And also Presto was giving them unsatisfactory performance, right? Because with StarRocks, they're getting 200 milliseconds. And also they had high availability concerns because of Presto's, leader follower architecture, right? You cannot really do HA with Presto. And then they moved to StarRocks. Um, their queries see an average of 6 to 7 times performance boost on the data lake, right? And P90 latency decreased by 90%. So that's a 10-fold gain, right? And also a lower operational overhead, right? So they completely ditched Presto out of their technology stack. So that's one thing that they need to deploy and maintain. And that's one thing their engineers don't need to learn, right? And with StarRocks Trino and Presto dialect support, the migration process was really fast because they didn't really need to change their SQL. So they deploy and connect to their Hive, and everything was working. So that's all I have. You can go to CelerData blog, sign up CelerData Cloud, join a Slack channel, give us a star on GitHub, or connect with me on LinkedIn. Uh, thank you. And if you have any question, please ask them in chat. I see some questions there. I know we're talking about Trino, but does it apply to Presto as well? Are there any differences worth mentioning? Um, they're very similar projects. Oh wait, some question here. Yeah, Trino was a fork of the Presto projects. I think 3-4 years ago. And they're very similar, but there are differences. Probably too many to mention here. So if you guys are interested, we can have a article that explain this. And let's look at the next question. Performance differences between StarRocks internal table and internal table query versus data lake query. So that's a great question. So StarRocks internal table is actually storage compute separated as well. So the only difference between StarRocks querying internal table versus querying data lake, it's only like in the tens of percent. Yeah, I think it's 15 or 17% of a difference when cache is not enabled, right? So there's not that much difference without consideration of cache. What data lakes does StarRocks support? StarRocks supports Apache Hive, Hudi, Iceberg, Delta Lake, and Pymon as a new one. How is the materialized view refreshed? So the materialized view, the refresh is by partition. So this materialized view is actually not real time. So it's by batch, right? It's by partition. Any other question there? Can StarRocks serve as a data lake house? That depends on how you define a data lake house, right? If a lake is S3 storage, then yes, because StarRocks itself is storage and compute separated. And also StarRocks file format is proprietary. It's not really proprietary, everything is open source, right? But StarRocks is you would rather use StarRocks as a query engine for your open data lake house architecture, right? If you don't have a data lake, you can use StarRocks as is, as a data warehouse, as a storage and compute separated data warehouse. I know StarRocks was forked from Doris. Is Doris able to do any of this, or StarRocks capabilities here unique? Um, yeah, so StarRocks was forked from the Doris project, like from a long time ago. Back then, Doris didn't even have vectorized execution, um, and we reworked I think 80 to 90% of the code already. So the two projects are completely different now. I've heard that they're doing something with the data lake, but I'm not really sure. I saw the term pipeline free data analytics. Um, on the CelerData side. What does it mean exactly? Uh, so pipeline free in this term is by using StarRocks, because StarRocks has the performance to take care of all of your analytics workload directly on the data lake. So you don't have to develop a data ingestion pipeline to another data warehouse purely for query acceleration. And that's where the term pipeline free come from. The CelerData Cloud do everything StarRocks can do for data lake performance. Yes, and more. The StarRocks have a plan to ingest the data into an open format like Apache Iceberg. That's actually already supported, Iceberg Sync and Hive Sync. Let's see. Uh, see another question. What is the storage used for this benchmark? I think it's the TPC-DS benchmark. Yes, it's object storage. It's not local. Why the custom format and how different from Iceberg? I'm not really sure about what custom format means. If you mean by StarRocks' own proprietary format, StarRocks' own format is more optimized for query. It's better performance. Have you compared it to Rising Wave? Actually, not much, but we can do that. We can do some more investigation and get back to you later. Is custom format good for low latency append? Um, StarRocks data warehouse can do real time analytics. Um, if you mean by that, and with local storage and everything handled locally, you can get much better data freshness. Not only data appends, but data updates, upserts, deletes as well. Where can we read more about on the caching layer? So go to StarRocks documentation site and search for data cache, and that's what you need. Okay, I think we handle all of the questions. Um, if we have any more question, please reach out to me on Slack or raise them in the Using StarRocks channel, or reach out to me on LinkedIn. Happy to discuss. Thank you. Hope you guys enjoyed. Thank you.